We speak on the minimal surface in M cross R. Harold?
Thank you. I'd like to talk about joint work with Bill Meeks. And the subject that we've been looking at are properly embedded minimal surfaces sigma in the product of a Riemannian compact two-manifold with the real line. So M is a Riemannian compact two-manifold. And today, since I'm going to be talking about these kind of surfaces, when I write this, I'll mean properly embedded minimal surface. And I'd like to try and explain to you the meaning of two theorems. Theorem 1, consider this situation, properly embedded minimal surface in this kind of Riemannian product. First thing is, such a surface has a finite number of ends in the sense of topology. A finite number of ends. Secondly, if the surface has bounded curvature, I'll explain what this means in a second, then it has linear area growth. And what does this mean? This means that if one looks at the area of the part of the surface between two heights, M cross minus R plus R, so this means the area of the part of the surface between these two heights, then this area grows at most like a constant times R, for some constant, in case sigma has bounded curvature. I was hoping I'd fit the two theorems on this blackboard. I was wrong. I wanted these two blackboards to work and leave these here. Let me try theorem 2 here. If sigma has finite genus, then sigma has bounded curvature. Now, from the point of view of topology, this is not very complicated. Sigma is a surface of dimension 2. To say it has a finite number of ends, if one adds the hypothesis of finite number of handles, finite genus, then it's just topologically a compact surface minus a finite number of points. That's what finite topology means. So in that case, it has bounded curvature. And this is a very strong geometric statement. For example, in particular, if the surface we're talking about, M2, has non-positive curvature. Imagine this surface is defined by a Fuchsian group acting on the hyperbolic plane. So it has a metric of curvature -1, for example. If this has non-positive curvature, then the minimal surface sigma has finite total curvature. And there's a nice formula for it, which looks like the Gauss-Bonnet formula. It's equal to 2 pi times the Euler characteristic of sigma. What I'd like to do today is try and give you some understanding for what these statements mean. Because stated like that, they look like really abstract theorems. What am I talking about? So I'd like to spend my time discussing what goes behind this by giving you examples and trying to explain this picture to you. Let me begin just by saying what some of the words here mean and just pointing out some obvious facts. When you consider a minimal surface in a Cartesian product like this, the height function is a harmonic function on the surface. So for this whole talk, I'll have this nice height function on sigma, which is harmonic. And that's going to be very important for working with this theory, is harmonic on minimal surfaces. Now, what is this height function? Well, I just mean the height that it's at. So if I take a point P in sigma, all right, P is equal to xt, where x is in m, then h of P is just the height, t. Since this is a harmonic function, the maximum principle applies. So if by any chance sigma were a compact surface, h would be constant. So the only compact surfaces in this theory are the surfaces of the form m cross t. So I'm really talking about non-compact, properly embedded surfaces. So if sigma is compact, sigma is equal to m cross a certain t naught. So really, compact surfaces aren't interesting in this theory. The finite number of n's. Let me just make one remark about that. The simplest kind of minimal surfaces one runs up against in Euclidean 3-space have an infinite number of n's. One of the most elementary surfaces was the Riemann's minimal surface, which he described by writing down explicit formula in terms of elliptic functions. And what this surface looks like from the quasi-geometric point of view, one takes planes at constant distance apart, and the surface is a geometric perturbation of this system where one puts catenoid necks between these planes, connecting them. And one does this from plus to minus infinity, etc. So one obtains a surface here invariant by a translation like this. Each of these planar ends is an end of the surface topologically. So there's an infinite number of ends. From the point of view of topology, what we're looking at here is a cylinder, and each end is just a puncture on that cylinder from plus to minus infinity. So the surfaces, minimal surfaces in Euclidean 3-space, naturally tend to have an infinite number of ends. So it's rather remarkable that in this space, one can prove that there's always a finite number of ends. Let me just make one remark about what this means to say bounded curvature. A minimal surface in a 3-manifold has the property that the principal curvatures are equal and opposite. The surface is curving at most one way as it is the other way. So if the curvature is bounded of the surface, the Gaussian intrinsic curvature, this means that the extrinsic curvature of the surface is bounded as well. The two are equivalent for minimal surfaces. So there's one fundamental fact that one should keep in mind when you think of bounded curvature for minimal surfaces is the following. So bounded curvature implies there exists some positive delta such that for all p in the surface is a graph over a disk of radius delta in its tangent plane, and that graph has uniform bounded geometry. So I'll just draw the picture. I'm not going to write that down. Here's p. Here's the delta disk in dimension 2. The surface has, it's really a graph over the entire disk of radius delta, and is close to its tangent plane, uniformly close. So that's what bounded geometry means. Okay, now I think I've explained at least all the words here. Now let me say something about what's going on. The study of the global theory of minimal surfaces in three manifolds, one looks at points where the curvature is blowing up. Where the curvature is not blowing up, one gets a nice picture of a local graph over a delta disk, and one controls the geometry. So to prove things like sigma has bounded curvature, one has to study where the curvature is getting big. Where the curvature is getting big, one can think of doing a homothety to make the maximum of the curvature 1 and study the surface after that homothety. And when you do that and pass the limit as the curvature goes to infinity, what you're really studying are minimal surfaces in R3, embedded complete minimal surfaces in R3. So the local theory, to study this subject here, you have to study the local theory is really the same thing as the global theory of minimal surfaces in R3. And they're properly embedded minimal surfaces that arise when you take limits like this where the curvature is blowing up by homothety. So what we've been able to do is, due to some recent results in R3, we've been able to attack minimal surfaces in these three manifolds and prove these theorems. So let me tell you what the two results in R3 are that play a fundamental role in this study. There's two theorems in R3. Theorem 1, suppose sigma is a properly embedded minimal surface in R3 that's simply connected. Then sigma is a plane or helicoid. It's equal to a plane or to a helicoid. Theorem 1. Theorem 2, due to Kolding and Minkowski, which is also a basic tool for proving theorem 1 here, says the following. The statement is rather technical, but I'll explain what the statement means, and we're going to work with it throughout this talk. Consider a family of minimal surfaces that are properly embedded in R3. So consider a family sigma n of properly embedded minimal surfaces in R3. One would like to know when there's some convergent subsequence of this that converges to something or other, some object, some geometric object. And that theorem gives a criteria to obtain such a compactness theorem. The criteria, which is called uniformly, locally, simply connected. Let me just write that down without telling you what it is for the moment. If this family satisfies this condition, then there's a subsequence of this family of surfaces that converges, in a sense that I'll tell you, to a minimal lamination of R3. Then there exists a sigma nj that converges to a minimal lamination L. It's a lamination by minimal surfaces. Now, what does this mean? I'll tell you in a few different steps how to interpret theorem 2, and the helicoid will come in to the explanation. First attempt at understanding theorem 2, what kind of convergence is this? A minimal lamination is almost like a foliation by minimal surfaces. So imagine you have some foliation by minimal surfaces, L, in this lamination. The convergence here means the following. There are Lipschitz curves that meet each leaf of this lamination in isolated points locally. These are Lipschitz curves, S, which is the singular set of convergence. It's where the curvature is going to blow up as you look at the subsequence converging to the leaves here. For every compact set, K, that's not in the singular set, but it's in a leaf, the leaves sigma n are converging just like graphs converge to k in a ck topology for any integer k. So away from the singular set, the convergence is geometrically as good as you want. And near the singular set, you can't say anything. Let's try and understand this one step further. Let's look at the helicoid. What is the helicoid? Well, one way to begin to understand the helicoid is take a straight line like the x3 axis, take a line orthogonal to it, and spin that line at a constant speed as you go up the axis. And you get the helicoid. So let's try and understand this. Suppose this is one period. So I started with this line, I turn around by 2 pi, and I come to this line. Then you go on further up and further down. When you're far away on this line, and you turn around by 2 pi, that's a very, very long curve compared to being close on this line. It's a very, very long helix. Therefore, it's going up very slowly. So the surface here is very flat. It's almost like a flat plane geometrically. And the further you go out, the closer it gets to a flat plane. It's like a staircase. It's almost not going up at all. As you come in, here it's vertical. So here the tangent plane has a normal vector that's horizontal. And here it's spinning very vertically before you go up the helix. And then when you go out this way, it's becoming very, very flat again. The normal vector is turned over. So here we see planes. Now I'm going to redraw the picture and keep this in mind. So here we see planes far away. 1, 2, 3. 1, 2, 3. And if we look at a cylinder around the axis, the x3 axis, we see a spiral that goes up here, goes around the back, goes up. But it's a double spiral. It's a double helix coming from the fact that this line passes through the origin here. So here we see this. So on this cylinder, we see a double helix going up. Now, this is a minimal surface. Call it sigma. Consider the family of minimal surfaces where one does a homothety of this surface by a factor 1 over n. Say this is the origin here. And one considers sigma n to be 1 over n times sigma. What does this look like? It's a family of properly embedded minimal surfaces. And what's happening? When you do this homothety, these planes that are far away, well, you come in, they get closer and closer together. But they look like, the further you go away, when you do this homothety, they look like planes until you get really near the axis. So what you see here is planes, but the distance, if this distance here was t, this distance is 1 over n times t. Then you get near the axis, and you see lots of fast spiraling near the axis. And you go away, and you see these planes, 1 over n times t. So when n goes to infinity, this converges to the foliation x3 is equal to constant. The limit lamination is a foliation of R3 by horizontal planes. The singular set is the x3 axis, S. And that's where the curvature is blowing up when n goes to infinity. So that's a very nice picture that explains this theorem at its best, the Kolding-Minkowski. Now, I didn't at all talk about this condition here. Just to make you realize that convergence like this is a very exceptional thing, let me give the simplest example I can think of, or a simple example, where this convergence completely fails. There's no subsequence that converges to anything. The Schwartz p-surface. Schwartz constructed a triply periodic minimal surface, which can be thought of as follows. Consider this polygon in R3. take a least area minimal disk with boundary of this polygon. There's a least area minimal disk with boundary of this polygon. The coordinate functions are harmonic on the surface, so Schwartz knew that if you have a straight line in the boundary, you can do Schwartz reflection and continue the minimal surface by reflection around that line. And you keep on going. Up. And do this for each edge that you have, and you get a nice triply periodic minimal surface, which one calls, for example, the Schwartz P surface. Now, what does that surface look like globally? You see, each of these things, when I continue around, will have a handle there. So I see lots of handles, triply periodic way. The surface is connecting these handles like this. And this goes this way, this way. What happens when you do 1 over n times sigma? Do the homothety to shrink this down. You see curvature blowing up everywhere. All of these handles here shrink down to very small handles with very big curvature. So the curvature is blowing up everywhere. It looks like this, et cetera, et cetera. There's no subsequence that converges to anything. So this condition of being able to say there's a convergent subsequence to a minimal lamination is a very interesting theorem. Now, what is this condition? Let me just tell you what it is. It means that you can cover the space by balls, ambient balls with fixed radius, so that each connected component of the sigma n inside the balls is simply connected. So one doesn't want to allow, for example, to have little catenoid necks in every ball that you can draw, like that. That's not a simply connected component inside this three-dimensional ball. So, for example, if the original surface was simply connected itself, this condition would always be satisfied. If the original surface doesn't have too bad a topology, one will often be able to satisfy this condition. And then one will be able to apply this theorem. Okay, now, these two results, the unicity of the helicoid and this theorem of Koldi-Minicozzi, are the basic tools that enables one to prove these theorems. So my goal now is to sort of try and indicate to you how this local theory has these global consequences. But before doing that, I'd like to show you this is an interesting subject by describing some examples. There are many, many examples of properly embedded minimal surfaces in MxR. So let me just talk about examples first to sort of motivate why one would even look at this subject. Okay, let's consider some examples. So consider the simplest space, the two-sphere cross R, where this has the round constant curvature metric. This is a round two-sphere. And there's one obvious properly embedded minimal surface in here. Suppose gamma is a simple geodesic of S2 cross 0. So imagine here's S2 cross 0, a round two-sphere, and take a geodesic like this, gamma, and just take the Cartesian product of this with the real line. That's a totally geodesic vertical annulus. That's certainly a properly embedded minimal surface. It meets S2 cross T in a simple closed curve, which is essentially just gamma at height t. That's the simplest example. Now, Pedrosa and Ritore wrote down a family of perturbations of this example where they tried to solve the isoparametric problem in S2 cross R and studied what were the rotationally invariant, under a certain sense, minimal surfaces. And they call them unduloids. What are these surfaces? Let me just point out something to you in Euclidean 3 space. If I take in Euclidean 3 space two geometric circles that are close together and in parallel planes. So just think of one circle right above the other. There's a soap film between them. It's part of a catenoid. It's a compact minimal surface with boundary of these two circles. It minimizes area. It's a minimum of the area function. There's another minimal surface bounded by these two circles, which is sort of obvious, which is a local minimum for area. It's the union of the two horizontal disks. It's not a global minimum for the area, but that's another minimal surface, which is a local minimum. If you look at the area functional on the space of minimal surfaces, if you have two local minimum, you have one of index 1. So there might be one of index 1 between them. And in fact, there is. It's another catenoid, which is the unstable catenoid, which goes far into the axis. So these two local minimum give rise to another minimal surface with this boundary, which has higher index, index 1. The same thing happens here. Without writing down formulas the way they did, one proceeds as follows. Consider this circle gamma. I want a parallel circle. So what circle am I going to take? I'll take the circle gamma t at height t. If t is small, I'm drawing a picture like this, not very realistic, then it's clear that just the part of sigma here between these two circles, gamma 0 and gamma t, minimizes area. It's a minimum for the area. So that's 1 sigma 0. There's another one bounded by these two circles, which is a local minimum for area. Namely, this is on the 2-sphere. So it bounds a disk on the 2-sphere, d0. There's another disk over here. But gamma here bounds a disk of d0. The other, gamma t, bounds the disk dt, which is just d0 at height t. That's a local minimum. So by the same kind of reasoning, there's one of index 1 between them, which looks like the catenoid that goes in. And as a matter of fact, it does look like geometrically this situation. An unduloid. Now it's bounded by two circles. One has an isometry of this space M cross R, S2 cross R, which is symmetry by this circle, gamma. So one can extend this to the other side and keep on going. And if I did a small perturbation, one gets, here's the sigma, gamma cross R, one gets a surface. Properly embedded minimal surface looks like this. So it's a properly embedded annulus. It intersects each S2 cross T in a geometric circle, constant geodesic curvature. Amazingly enough, these surfaces really come from the Delaunay surfaces in R3 of constant mean curvature. This was not in the paper of Pedrosa and Ritore, but there's an obvious way to go from constant mean curvature annuli or tori in R3 to minimal surfaces in S2 cross R. And if you start off with the Delaunay surfaces of mean curvature 1, say, you get these unduloids. Let me give one other type of example of higher topology. This was topology in annulus. Namely, consider the 2-sphere. We had gamma. We have these two disks, D0 and D1. Consider a geodesic triangle on the 2-sphere going to the center of this, angle theta, take theta equal to pi over k, k in integer greater than or equal to 2. Okay? That gives an obvious geodesic triangulation of the two-sphere, etc. But I want to work on this triangle here. Now I'll put this D0 here, over here, just for the picture. That's a D0. And this is the triangle. Now I'll take a vertical geodesic and go up a height t here. And take this part of this geodesic on gamma. We have a geodesic polygon here. This geodesic polygon, you can solve the plateau problem. It bounds the least area disk, which in fact is nothing else but a graph over this triangle here, the interior of this triangle. So one has this least area disk, and one can do symmetries around the geodesic boundaries of this disk. This was D0 here. For example, one obvious symmetry would be to do symmetry around this vertical geodesic here. If I do symmetry around this vertical geodesic, I go from D0 to D1. And I get a graph over this triangle. And this circle here continues this way, but on the other side. I'm not going to draw it. I get the graph on the other side. I can also do symmetry around this geodesic. If I do symmetry around this geodesic, this thing goes to a graph, again over D0. This edge here goes to an edge here. And I get something like this. And this becomes this. And if you continue around the disk here, we'll get a graph over the interior of D0, which just looks like a standard sort of thing, bounded by, in fact, a circle up here and a circle down here, because one has the other side too. As soon as I did the symmetry here, this becomes a graph. This is a graph over this, but now this goes to this by symmetry over this. So one fills up the whole two-sphere, and when doing this, one gets a circle at height t, a geodesic, a circle at height minus t, a geodesic, and in between, a surface of a certain genus, because one has a critical point here of index k minus 1 in D0, another critical point of index k minus 1 here, so one knows the topology of this surface. For example, for k equals 2, one gets a 2 torus minus 2 disks. Disk up here, disk down here. So one should think of this, for example, as 2 critical points of index 1. They're not at the same height as indicated in this picture. This is very reminiscent of what Blaine Lawson did in his thesis in the 3-sphere. Exactly like this, that he constructed minimal surfaces in the 3-sphere by doing this kind of plateau kind of solution for geodesic triangles and doing symmetries. Now, this surface has a compact boundary here. It's this circle and this circle. So one could do translation and construct a properly embedded surface, which would be periodic. Or if one wants to have finite topology, one could let t go to infinity here. And show that as t goes to infinity, this limit surface exists. Just the way Shirk surface exists in R3. So one does a little work, lets t go to infinity, down here to infinity, and one gets a surface with one top end asymptotic to a gamma cross r, one bottom end asymptotic to gamma cross r, properly embedded, and in between, the same kind of topology as here. The 2 critical points stay the same. So one has many examples of this type, which shows that you have many surfaces that are geometrically interesting, of all genus, all topology, etc., properly embedded. This is just S2 cross R. One can do the same thing in the quotient of the hyperbolic plane by Fuchsian groups. Take a compact Riemann surface of curvature -1. There are many beautiful groups and surfaces like this that one can construct coming from that sort of geometry. Okay, so that's the examples. Let me now say some words about these theorems. Okay, so now let me consider, for example, proving linear area growth. Linear area growth. One of the ingredients that's very important in this kind of study is the flux. Let me say some words about the flux. If you have a Riemannian manifold, for example, sigma here, which is compact and with boundary, and you have a harmonic function on sigma, then the flux across the boundary is 0. That's the boundary of sigma. The flux across the boundary of sigma is the scalar product of the gradient h with the conormal going out. So nu is the outgoing conormal. So if I apply this to minimal surfaces in M cross R, what I'll look at is the part of the surfaces between two heights, M cross T1, M cross T0. Since it's properly embedded, the part of sigma between these two heights is compact. So if it's a regular value of T1, I'll get some, that's sigma T0, T1, the part of sigma between here. It has compact boundary. I have a harmonic function, which is a height function. So the flux is 0 across the boundary. That means the following, that if I take the conormal vector, nu, going up, that's tangent. It's not the same conormal as here. That means the integral of grad h dot nu, this boundary here, sigma intersect M cross T0, is equal to the integral of the same quantity at height T1. Sigma intersect M cross T1. The flux is constant on a minimal surface because this height function is harmonic. Okay? Now, what does the flux measure? For example, suppose the surface was almost vertical here. If the surface was almost vertical here, then this conormal here, which is length 1 and tangent to the surface, is almost gradient h. Gradient h is just the vector d dt. It's a height function. So if it's almost vertical, gradient h is almost the same thing as nu. So the flux is just the length of this level curve when it's almost vertical. And when it's almost horizontal, then the flux is very small compared to the length. So that's some geometric idea of what the flux is measuring. When it's very horizontal, if the curve is short, the level curve is short, the flux is very small. If it's near the vertical, the flux is measuring the length of the curve, the level curve. Okay. Now, let's understand, at least in some simple cases, linear area growth. Suppose I have sigma properly embedded in M cross R, and it does not have linear area growth. Linear area growth. We'll get a contradiction. So we have some sequence of points Pn and sigma such that the area in the part of sigma between heights Pn minus 1 over n, this is the height of Pn minus 1 over n, and the height of Pn plus 1 over n. the area of the surface sigma in there is greater than or equal to n. Since M has bounded curvature, that means there are more and more sheets of sigma. Since sigma has bounded curvature, sigma has bounded curvature, this means there are more and more sheets of sigma passing in this slab. So let's translate this whole situation down to height 0. Let's consider, that's an isometry, translation t by minus h of Pn, that height, of sigma. And call that surface sigma n. I just translated this down so the point Pn here goes to height 0. And now I'm going to look at what happens for this family of surfaces between minus epsilon and plus epsilon in height. So here's m cross plus epsilon, m cross minus epsilon. And here I see an area which is greater than or equal to n of sigma n. And as n goes to infinity, this area goes to infinity. Now, these surfaces are properly embedded, each sigma n, and we have curvature bounds. So it's not hard to see that there's a subsequence of these sigma n's that converges to a minimal lamination. The subsequence of sigma n converges to a minimal lamination. The spirit behind this is, when you have bounded curvature, you write it as a graph over a delta disk in a tangent plane. You have an infinite sequence of graphs like this. They're minimal graphs. They're all bounded because you have bounded curvature. So some subsequence of these graphs converges to a minimal graph. The minimal surface equation is an isoelliptic equation. So you have this kind of local compacity. And then you piece things together to get a lamination limit. Now, what does that mean? What's the problem with this sort of limit? I claim that one has m cross 0 is a leaf of this lamination. M cross 0 is a leaf of L. Why? Suppose it wasn't. If it wasn't the leaf, here's the horizontal. Here's this leaf L in L. Passing to a point here. Suppose it's not horizontal here, this minimal surface L. It's a limit of the sigma n. So in some ball around here, this is bounded geometry, this L. So the intersection with this ball is just some transverse curve here. We get some surface here, which has a fixed vertical flux, epsilon 0. The conormal vector here to this surface makes a fixed positive angle with the d dt. That's far from pi over 2. So the flux here is like the length of this times this angle. Now, these surfaces, sigma n, are converging uniformly to this nice disk here. So nearby here, I'll draw the picture in dimension 1. We see pieces of sigma n converging in the CK topology to L. So the angle of the conormal here is converging to this angle. So the flux of this piece of sigma n here is at least, say, epsilon 0 over 2. For each sheet of sigma n that's converging to L, I see a definite amount of flux, which is positive. But since we have an infinite area for the sigma n, we have an infinite number of sheets. So I see an infinite number of sheets here of sigma n as n goes to infinity, more and more sheets converging to L. But each sheet gives a flux epsilon 0 over 2. That means the flux of sigma n goes to infinity as n goes to infinity. But what is sigma n? I took sigma and I translated down. Translation doesn't change the flux of sigma, and we saw the flux of sigma was constant. The flux of sigma is constant, positive number. So this is impossible. So that means that this L here, this limit leaf, is the horizontal M cross 0. Now, in general, that's where the work begins. There's only one case where it's easy to see this is not possible, namely when M is equal to the 2 sphere. Now it's easy to see this can't happen. When M is higher topology, it's more complicated. When M is the 2 sphere, sigma n has more and more sheets that are becoming near the horizontal here. They're converging with their tangent plane to the 2 sphere. But now I can lift, by the usual holonomy of foliation applied to a lamination, I can take a path between 2 points P and Q in the 2 sphere and lift it onto sigma n, P tilde Q tilde, for n sufficiently large. And this lifting here, since this is simply connected, doesn't depend on which path I choose. So I can lift the whole 2 sphere into sigma n. Well, that means sigma n is a 2 sphere. Contradiction. Okay? So that's the idea when it's compact. In the 3 minutes I have left, I'd like to show you why the unicity of the helicoid and this Kolding-Minkowski business enables one to prove the bounded curvature theorem. Let me just say some words about that. Suppose you take a surface of finite topology, properly embedded minimally in M cross R. Finite genus means finite topology here. Finite topology. So this means it has a finite number of annular ends. So to show that the curvature is bounded, you have to show that the curvature of each annular end is bounded. So take some annular end A, an annular end of sigma. Suppose the curvature blew up. I'd have a sequence of points Pn in A where the curvature was tending to infinity. Translate Pn to height 0. Now we're at height 0. Call it Pn tilde. Now the curvature is going up to infinity. Now, this Kolding-Minkowski theory plus this theorem of unicity of the helicoid means that one sees a helicoid forming here. A real honest-to-goodness helicoid. As n gets bigger and bigger, if you can take a vertical cylinder here, one sees a helicoid forming, a double helix here intersecting this vertical cylinder. The helicoid has to be vertical because if the helicoid were tilted, one would get infinite flux. The flux would go to infinity, and that's not possible. So it's really a vertical helicoid. And outside of the points where the curvature is blowing up, one sees a minimal lamination forming. So if one looks at the level curve here, one gets some level curve here like this. And one can prove that there has to be another point on the level curve where the curvature is blowing up too. So one sees another helicoid forming here. So one sees a double helix here and a double helix here. Well, what do you do when you see a double helix? Well, we take a path in sigma n going here, go up once, come here, go back in sigma until you get to the next point up here, and then come back here. So what we did here was we constructed a curve like this. A simple closed curve gamma in A. That simple closed curve either bounds a disk in this annulus or it doesn't. It can't bound a disk in the annulus. You prove that because if it bounds a disk, this helix here has another sheet in between because it's a double helix. There's another sheet here, another sheet here. So you have another curve going here. So there's a sheet in between, but in this sheet I can just take an arc that goes like this, and that arc can never leave the convex hull of this curve. So one gets a contradiction thinking about that. So it can't bound the disk. So it's a generator of the fundamental group of this annulus. That means that its flux is the flux of the annulus. But this curve here is almost horizontal. This curve is almost horizontal. And this is a very short curve because it's a helicoid that's really very, very curved here. So its flux is going to 0. But the flux is an invariant, so it's a contradiction. Thank you. That's that.
Thank you, Harry, for the presentation.